So I want to work some example problems on RL and RC. We're going to initially just kind of work through some of these and kind of show you how to set them up. The basic problem that we're going to be working with is, remember that we have that general equation, and for the general equation you have to find the initial value, the final value, and tau. So my goal in working through these is to illustrate for you how to find the initial value, the final value, and tau, and then I'll leave you to plug those into the equation in order to get the final version of the current. The other thing to remind you of is in this problem, for example, we're actually asked to find two things. We're asked to find I1 of t and I2 of t, and so that's here and here. The only thing that we can actually solve for initially is I1, because that's the current through the inductor, and that's where we have the initial condition constraint. So we will have to solve for I1, and then that'll enable us to solve for I2 using KCL, KVL, and the definitions in the circuit. So the first thing to do in any problem like this is to solve the problem for t less than 0, because that will give us the initial condition on the inductor. So we can always make the assumption, unless told otherwise, that for t less than 0, the circuit has been sitting for a very long time. So what that means is that when you sketch that circuit for t less than 0, you can show inductors to be short. So here's what that circuit will look like. And then the inductor is short. And so all we have in this branch here, we just have a 6K resistor. But remember, it's this branch with I1 that actually contains the inductor. And so what we really want to solve for, and remember this is at 0 minus, so before the switch moves, immediately before the switch moves, what we want to solve for is the current in the 6 kilo ohm resistor. So a number of ways to do this. We could combine the 6 and the 2 in parallel, or we could do a source transformation on the 40 volt and the 500 ohms. I think I'll do that. That'll give me a current here that's equal to 40 over 500 amps. And then that'll put the 500 in parallel with 2000 and the 6000. 500 in parallel with 200 should give 400 ohms. So I have looks like 0.08 amps, and that's going to divide between a 400 ohm and a 6,000 ohm. So if I do that, I get I1 at 0 minus. Remember, it is the total current times the one you don't want, which is the current through the 400 ohm resistor, over the sum of the two. Okay, and we can do that really quickly on a calculator, or I'll leave you to do that on your calculator, but that'll give you the initial value. Okay. Now the next thing we have to solve for, we need two more things. We need tau, and we need I1 at infinity. So first of all, let's solve for tau. So for tau, we need to illustrate the circuit for t greater than 0, which means this switch is open. So what I have are these three elements in series, the 400 millihenry, the 2 kilo ohm, and a 6 kilo ohm. So here's 2K, Here's the 6K. Here's my inductor. What was that again? 400 millihenries. Let me go ahead and write that as 0.4 henries. So remember that tau by definition is L over R. So that is 0.4 over 6 times 10 to the third. And once again, I will let you find that actual number. And the final thing that we have to solve for is I1 at infinity. Well, if you look at this circuit, basically in this circuit, the current at infinity will go to 0. Okay, so as the current goes to 0, then basically at infinity your value goes to 0. So now we can actually solve for I1 of t. Okay, and I'm going to let you, because I want you to do some work on this homework assignment, I'm going to let you look up the formula that involves I at infinity, I at 0, and tau. I'm going to let you look that up, and I'm going to let you make these substitutions so that you can have some practice at looking up that formula. Remember, the formula is actually given in your book as x of t, and it's in terms of these three variables. So you need to rework this problem following the guidance given here so that you're sure you know how to do it. Alright, here is another problem, and it's almost exactly the same. So we'll look at this and see kind of what this looks like. It's also an inductor problem. You're asked in this problem to find this voltage V naught. Oh, let me go back to the previous example really quick. Okay, remember we're also asked to find I2 of t for t greater than or equal to 0 plus. And I2 of t is shown here. So let's come down to our circuit for t greater than 0. This is I1 of t, and I2 of t is shown here. I2 of t. And this was I1 of t. So of course all of these things are in series, so the current through everything has got to be the same. We have already solved for I1 of t. You notice that I2 of t is drawn in the opposite direction. So to find I2 of t, we just need to say I2 of t is negative I1 of t. And that's all we have to do there. And by the way, this current I2 of t, because it's not the current through an inductor, it's the current through a resistor, it is allowed to change instantaneously at t equals 0. So as you come back, if you solve for I2 at 0 minus, you will find that I2 at 0 minus and I2 at 0 plus are not equal. So how would you get I2 at 0 minus? Well, we found the current through the 6,000 ohm resistor here, and so using KCL we could easily find the current through this 400 ohm resistor, and then we could use a current divider between the 500 ohm and the 2000 ohm to get the initial current through the 2000 ohm resistor. So that's how you would find I2 at 0 plus. That's not really an RLC problem, that's more of a Kirchhoff's current law problem, but I wanted to illustrate it for you just so that you would have that available. Okay, now let's look at this problem. It's very similar. So let's first of all solve for the inductor current for t at 0 minus. So here's my 240 volts. For t less than 0, the source is connected. The 6 ohm resistor here is not in the circuit for t less than 0. It's just dangling there unconnected. So we'll just leave it out of our t less than 0 circuit. Here's 40 ohms. And the inductor here is a short. Here's 10 ohms. And we'll just go ahead and define this as being the inductor current at 0 minus. Okay, so doing a little bit of manipulation, let's see. We'll combine these two in series to get 16 ohms. You should probably resketch the circuit if you're going to do that. Then we can do a source transformation. This will be 240 over 16. And then we'll have our 16 ohms in parallel, our 40 ohms in parallel here, and our 10 ohms here. And remember, this is the current we want, current at 0 minus. So now, a couple of things you could do. You could combine these two in parallel and do a current divider, which is probably what I would do. So let's see, 16 parallel 40 is going to be 16 times 40 over 16 plus 40. And I'll allow you to do the algebra there, and we'll just call that our equivalent. And you can do the algebra and fill in the numbers. And so then that means that the current through the inductor at 0 minus is basically found from a current divider. So we'll take this guy, which is equal to 15. So we'll take 15 amps, and we'll do the current divider, which will be whatever that equivalent resistor is, over the sum of it and the 10 ohms. Okay, and that'll give you IL at 0 minus, and once again I'll let you plug in the numbers. Okay, the next thing that happens is the switch moves, and so when the switch moves, it moves to position 2, and the source is out of the problem. So let me see if I can squish that in right here before I move the page. So here's 6 ohms, 4 ohms. So this is my circuit for t greater than 0, greater than or equal to 0 plus is another way to write that. Then I have 40, and here's my 72 millihenries. The inductor is in the circuit now because we're looking at the circuit for t greater than 0, and so we have to model those transient effects. Okay, now what I have to do is I have to find tau, and I have to find the final value of the inductor current. Well, once again, for t greater than or equal to 0, the inductor current at infinity is going to eventually go to 0 because it's going to drain all of its energy through the resistors. So that's easy. So now what I need to do is find tau. So to find tau, I need to reduce the circuit to a single resistor and a single inductor. And I already have a single inductor, so that's not going to be a problem. So what I need to do is simplify and combine all the resistors. So there's 10 ohms, there's 40 ohms, there's my 72 millihenries, and there's 10 ohms. So 10 in parallel with 40 is 8. So that then gives me 72 millihenries and 8 ohms and 10 ohms, which gives me 72 millihenries and 18 ohms. Okay, so now I can solve for tau because I have L and I have R. So once again, I'll let you get a number for tau. You've now got what the inductor current is at infinity. You've got what the inductor current is at 0 minus if you do a little bit of that algebra on your own. And so that's what that problem looks like. Okay, the final example that I want to work today is I want to look at a capacitor problem. So here's our capacitor problem. It's also a switch problem. And we're asked in this problem to find the capacitor voltage. Oh wait, let's go back one more time and look at this circuit. So what I've actually solved for when it's all said and done is in the circuit I have solved for this current IL of T. So that's what you're going to actually have as your answer. Now the T greater than 0 circuit, if we go to this point right here, what I actually want is I want this voltage. Actually, let's come up to this step. I want this voltage. That's what I'm actually asked to find in the circuit. So what I have is I have I of T. That's what I actually found. So if you look here, it'd be pretty easy to go to this step where the 6 ohm and the 4 ohm were combined. That then makes this V0, the voltage across the 40 and the voltage across the 10. You have two options. Probably the easiest option is to come to this step where I combine those two because they are in parallel. So that voltage drop is still going to be V out. You have IL of T. So finding V out, that's just going to be a simple Ohm's law. IL of T times 8 ohms. Okay, so that should be a really simple calculation. And it will be a function of time, notice. Okay, so that's how to find the voltage once you have the current. Okay, now back to this problem. Now, capacitor problems are a little bit different because under DC conditions, capacitors look like open circuits. And the other thing that you do in a capacitor problem is, like in the previous problems where we had to solve for inductor current, in a capacitor problem we have to solve for capacitor voltage. So we do this the same way. We look at the T less than 0 circuit. That'll be 150 volts. And it really, really will serve you well if each step of the way you will redraw the circuit. And this also helps us a great deal when we grade because we can follow what you're doing. Some of the stuff that I'm getting submitted on exams, just from an external point of view, just looks like nonsense. There's no logistical path to follow what you're doing. There's stuff all over the page. There's no figures drawn. Nothing is labeled. That makes it extremely difficult to give partial credit. All right, so looking at this problem, the capacitor under DC conditions, because it's been sitting for a long time, circuit's been sitting for a long time. So the capacitor looks like an open circuit, which means there's no current flowing here, which means that this 150 volts is going to appear across the open circuit. So we have BC at 0 minus is 150 volts. Okay, so now we let the switch move, and now we need to sketch the circuit for T greater than or equal to 0 plus. And when we do that, we will have 40 nanofarads, 5K, 30K, and 60K. And our V at infinity, which is the other thing we need, like in the previous inductor problems, because after the switch moves there's no source, so our V at infinity is going to go to 0. And so what we need now is our tau. So in order to get tau, we have to reduce down to a single capacitor and a single resistor. So we'll have 40 nanofarads. And let's see, keep our 5K here. And the 30 is in parallel with the 60. So that'll give me 20K. And then I can do the series combination there, which will give me 25K. And now I've got my circuit reduced to a single capacitor and a single, So I now have my circuit reduced to a single capacitor and a single resistor. So now I can calculate tau. It's just going to be R times C, going to be 40, 10 to the minus 9, 25, 10 to the third. Okay, and I'll let you finish from here. So you're going to use that same equation that we used previously, except instead of attempting to find a current, you're going to find the capacitor voltage. And so for x of t, you will substitute capacitor voltage as a function of time. And then that's all they're asking for in this particular problem. So you're pretty much done with that once you get that done. This problem is almost exactly identical. It basically, you're being asked for the capacitor voltage, and so you would do it exactly the same way. You would first draw the circuit for t less than 0 when the switch is over here. That capacitor will look like an open, so what you're really trying to find is the voltage across the 3.3 and the 2.7 K resistors. You can either combine those and use Ohm's law, or you can use current divider, find it through one of the resistors, and use Ohm's law on a single resistor. Either one of those techniques will work to get you the voltage at t equals 0. So what I want to talk about a little bit is the t greater than or equal to 0 circuit. Okay, for the t greater than or equal to 0 circuit, you'll have your voltage here, and you will have solved for that using the same approach that we did previously. What is that approach? Realizing that the capacitor voltage at infinity is going to go to 0 here because there's no source. Combining these resistors in series and parallel with this one to get a single value of R, and finding the RC time constant. Once you do that, one of the things that that you're being asked to find is you're being asked to find this current I of t. So once again, there's a number of ways, and what you have is you have V of t. So there are a number of ways to find that. I guess what I would do is realize that this capacitor and this 3K resistor are in parallel. So this is also VC of t. And then that's going to form, you have two choices. You could combine these two, the 2.4 and the 3.6. That would give you 6 kiloohms. And so now everything in the circuit is in parallel and would have the same voltage VC of t across it. So this voltage is VC of t, whatever that was. So your current I of t is just going to be your 6 kiloohms times VC of t. So that will allow you to get I of t. Now I will say in all of these problems, you're going to end up, in the 4 problems we worked so far, you're going to end up with a constant times an exponential decay. The constant will be the initial condition, and if you don't get that particular result, then you've made an error somewhere. So all you really have to do to work these problems is to look up that generic formula, that general formula. Follow the steps that I've shown. You should be able to work all the problems through 7.24. So the next video will illustrate, starting with problem 7.35, what you do when you have sources after the switch moves to t greater than 0. It's actually exactly the same. The only difference in a problem like this is you will not get a non-zero current or voltage at